build an XGBoost model to predict the presence of breast cancer. Extreme gradient boost is a supervised machine learning method that builds tons of small decision trees one after another, where each new tree is trained to correct the remaining errors of the trees built so far. This is one of the most sought after machine learning models in the data science world, and it has so many moving parts, so let's break it down with Python. Before we get started, make sure to check out part 1 of this video for a full XGBoost breakdown. And with that, let's get coding. As always, we must start by importing all of the necessary libraries. Today we have XGBoost to train the classifier itself, and 3 tools from scikit-learn to get some data, split that data, and evaluate the model. After that, we're loading in our breast cancer data, which is a binary classification dataset built into scikit-learn. This is just a tabular dataset where each row represents a different patient, and there are tons of feature columns to represent different characteristics about that patient. And at the end, there will be a target column which specifies if that patient has breast cancer or not, and this is what the model is trying to predict. Next, we're splitting our dataset into training and testing sets. Firstly, we're allocating 80% of the data for the training dataset, and this is the part of the data that the model can learn from and see while it's being trained. Then the other 20% goes to the testing data, which we will use later to evaluate the model's performance on unseen data. Now, here is the big moment where we're actually defining our extreme gradient boost classifier. The moment we define this XGBoost model, we are building a very specific kind of predictor that creates a boosted ensemble of decision trees, where the final model is a sum of many such trees built one after another. Each tree here is deliberately weak and simple on its own, but it's built to correct the mistakes of the current model. So once hundreds or even thousands of these corrections are stacked on top of the baseline model, the ensemble becomes extremely strong. The objective setting means the model will be trained for a binary problem and is asked to produce a probability that can be interpreted for one of the classes. This automatically ties the training to a probability-based loss function, so the model is incentivized not only to be correct, but to be appropriately confident. At a deeper level, this is where XGBoost learning from mistake mechanism truly lives. It starts with an extremely simple baseline model that is the best possible guess at the chosen loss. And then for every training example, it asks, if I nudge my prediction slightly up or down, how does the loss change and by how much? And this produces a key signal called the gradient that gives precise instructions of how the prediction should change. Each new tree is built then not to create any predictions from scratch, but to look at the gradient and create a new tree where the loss is lower. And this entire process is called boosting, which is an iterative refinement where the model keeps looking at what it could do better even when previous trees have already done their part. The choice of n estimators here is basically defining how many corrections we allow, because each correction is a new tree added to the ensemble. More trees tend to mean more opportunity to refine the decision boundary, but can also risk overfitting. So here we're choosing the sweet spot of 300 trees. The learning rate metric is the size of each correction that happens. The intuition here is that a lower learning rate forces each tree to make a smaller contribution to the full model, which usually improves generalization and stability. The max depth setting limits how complex each tree can be. Here we are limiting the depth to just 3, so each tree can only represent a simple structure. The ensemble's power comes from stacking many of these small trees on top of each other rather than just building a big complex one. Then the sample settings intentionally add randomness into the model by bootstrapping the data and the features that each tree can look at. And this prevents the boosting process from latching too hard onto a specific feature or set of examples. And the regularization setting penalizes the model when it gives very large weights to any given leaf, so the tree's corrections stay modest unless the data really calls for a bigger change. Finally, the evaluation metric setting is telling XGBoost to evaluate the model using logistic loss. This is very typical for extreme gradient boost models. When we fix this model on the training data, we are triggering this whole boosting process. Tree 1 learns the biggest and most obvious corrections from the baseline prediction, tree 2 learns what still needs correcting after tree 1, and so on and so forth. And the ensemble becomes a layered function where different trees specialize in different patterns. And as we're training our model, here's an example of just one of the trees that was created. Finally, we are predicting on our testing dataset from before, and we're creating 2 different types of output. yprob is the model's raw probability prediction that the patient does have breast cancer between 0 and 1, and ypred uses a threshold, typically 0.5 by default, to turn that probability into a simple yes or no answer. And then we print accuracy and ROC-AUC to give us 2 complementary views of performance. Accuracy tells us how often the model's prediction matched what actually happened, and ROC-AUC tells us how good the model was at separating classes. So here are the evaluation metrics for the simple XGBoost model. And just for fun, here's the feature importance chart. Ultimately, this was an extremely simple example of an XGBoost model, but these models really hold so much power in the data science world, and I highly encourage you to learn them. That's all for today, but don't forget to save this video for your next XGBoost model and follow for so many more breakdowns. See you in the next one.